Hello and welcome to lecture 22 of the course Computational Complexity. This will be a rather brief lecture, perhaps about 10-12 minutes, and we will see what is called Ladner's theorem, and we will see a high-level outline of one of the proofs for the Ladner's theorem. Okay, right. So we already know that P versus NP is a big problem. It's a big open question, right? We do not know whether P is equal to NP or whether P is a strict subset of NP, right? So now the question is, suppose P is not equal to NP. What are the problems that are in NP but not in P, right? So we know that NP complete problems cannot be in P, right? If P was not equal to NP, because if NP complete problems was in P, were in P, then P would be equal to NP. For instance, if SAT was shown to be in P, then all of P is equal to NP. All of NP is equal to P. So for sure, if P is not equal to NP, then SAT and other NP complete problems like clique, three colorability, all of them are not in P. So then the question is this. So now let's take, so suppose P is not equal to NP, right? So now let me draw a Venn diagram. Suppose this is NP, okay? And suppose this is P, the part that I'm shading in blue. Suppose this is P. Okay, this blue shaded part is in P. Now, is it the case that so suppose this is NP complete. So maybe I'll just write NPC. Sorry, maybe I'll just write NPC. So NP is this whole thing. This whole the entire thing, the big circle here is NP, right? So now suppose this is NP complete. So this green shaded part is NP complete. The question is, are there, so we know that the NP complete languages are certainly not in P if P is not equal to NP. So what I want to ask is, are there languages in the middle or in the intermediate region? So like in the light blue shaded region, is this region empty, or are there languages that are in the intermediate zone, right? So this part is called, so NP is this whole thing, and this middle part I am calling it NP intermediate, okay? So given that P is not equal to NP, we know that P and NP complete are disjoint. Now, does NP constitute of only P and NP complete, or is there an intermediate zone? That is the question. So is the light blue region in the middle? Are there languages there, or are they empty? This is the question. So is there in other words, is there an NP complete language? Sorry, is there a language that is not NP complete, that is in NP but not in P? So in other words, is there a language that is in NP but not NP complete and not in P? That is exactly what is called NP intermediate. Are there NP intermediate languages provided P is not equal to NP? This is the question that is answered by Ladner's theorem. So what Ladner's theorem says is that if P is not equal to NP, yes, there are NP intermediate languages. There are languages that are neither in NP complete nor in P, right? So I'll just give you a very brief high level idea, because the proof is a bit technical, and the techniques used are diagonalization mainly, and we have seen already time hierarchy and space hierarchy where we use diagonalization, okay? So I believe we could just, so I'll just give you a high level picture of this proof. And there is another trick used in this proof. That trick I will explain in a bit more detail. Okay. That trick is called padding. Okay. So what is SAT? SAT is an NP complete language, right, where you're given a Boolean formula, you have to decide whether it's satisfiable or not. Now suppose I write phi is a SAT instance, okay, and to write phi I require this much, the formula takes this much length, okay, and usually in our usual terminology n is the length of the input, and what we know is that n, there is no polynomial time algorithm in the length of the input. So if this is the input length, right, let us call it n, then there is no polynomial time algorithm in n, right, so there is no n power k time algorithm for any constant k. Now what I can do is to do something like this. I could take a special symbol, or I can even do it with some ones and zeros, right. Maybe I can make a new special symbol, let's say hash, right, and I can add a lot of hashes. Maybe I'll just write hash star, okay. So the first part is exactly the same, right, n of length n, which is the same formula phi, and the hash, I'll just change the hash to red color so that you know the distinction. So I'll just make it long just to, so the blue part is just the formula phi, and now there is a red part that is attached to the blue part, right, and now the whole length, right, the length of this whole thing, let us say this is n prime, okay, right. Now n prime is significantly bigger than n, right, because we added a lot of hashes to the end. So in this picture it looks like maybe slightly more than 2 times bigger than n, but think of n prime being much bigger than n, okay. So think of n prime being, let's say you can add much more, not even a constant time, maybe n prime could be exponentially longer than n, right. So in that case, now if I have to decide on whether, so there is a Boolean formula here phi followed by a bunch of hashes. Now I have to decide if phi is satisfiable, but now the problem length has grown so big. So the running time to decide this, so if the running time of deciding SAT, let's say there is an exponential time algorithm by trying out all the possible assignments, right. So here also we can do that, but now that requires 2 power n time. But when you measure the time as a, so suppose n prime is, let's say 2 power n, right. So now what happens, suppose if n prime is 2 power n length, now an algorithm that runs in 2 power n time is linear in this, right. So an algorithm that runs in order 2 power n time is now a linear time algorithm, right. It is just constant multiplied by input length, because the input length is now so much bigger than it is actually it's actually 2 power n, right. So, or it is constant times n prime, right. So what I am saying is that if n prime is sufficiently long, then now it is a linear time algorithm. Linear time means linear time is obviously polynomial time, right, because it's just a linear factor. So by adding enough of these hashes, now we can bring down the complexity of the problem, because the complexity is measured in terms of the input length, and by blowing up the input length, while not really increasing the problem size itself, right, the actual problem is still only n size, right. So by blowing up the input length, but keeping the inherent problem size the same, but the actual representation length, by blowing that up, we are now when measured as a function of the input length, the problem becomes now linear time or polynomial time, right? So this is what is padding. So by adding padding is just about artificially increasing the length of the input, so that artificially increasing the length of the input so that when measured as a function of the input length, the problem now becomes easier, right? So from exponential time now we went to linear time, which is polynomial time as well. So this is padding. So you saw how to go from exponential to linear time. Now the same trick is used in the proof of Ladner's theorem as well, right? So it takes SAT and adds a bunch of hashes to the end of SAT and tries to make it easy, right? So the assumption, again, the starting assumption is that P is not equal to NP. So SAT cannot be solved in polynomial time, right? So SAT requires more than polynomial time, right? It could be exponential or sub-exponential, something less than exponential also, but certainly not polynomial time. So now we want to pad SAT by enough number of hashes so that it no longer is NP complete. The complexity comes down from the NP completeness. But we do not want to pad it so much that it becomes polynomial time. So here we padded it so much so that it became linear time. So that is something we do not want. We just want to make it not NP complete, but we also do not want to do it so much that it becomes comes down to P, right? And so that is a challenge. So you want to exit this green area, but do not want to fall into the bottom dark blue area, but want to remain somewhere in the middle light blue area, right? So starting from SAT, we have to pad it enough so that it falls in the middle light blue area, and this is what is the proof. The proof is all about. So it figures out how much exactly to pad by, so that it comes out of NP complete but does not fall into P. That is the idea of the proof, and it uses diagonalization as well, amongst other things, right? So the diagonalization is used to show that it is not in P, right? So I'll just give you some candidate problems which as of now we do not know whether they are in P, and we also do not know that are not NP complete. So most people believe that P is not equal to NP. So people think that these are problems that are candidates to be the NP intermediate problems, right? So I'll explain the two problems. One is graph isomorphism. So what is isomorphism? Isomorphism is saying that these two are the same graph. So it is just two graphs, and whether these two graphs are the same. So that is a bit abstract. So I have an example. So I have three graphs here, right? The blue, the red, and the black. In fact, they are all the same graph. They are all isomorphic to each other. So let's see why they are isomorphic to each other. So I will again, I have not practiced this, so you can see the complexity involved. Right? So let me just label the blue graph 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So isomorphism means that the second graph, when we say that the blue and the red graph are isomorphic, it means that the second and third graphs, the blue and the red graphs are the same graph except for some rearrangement of the vertices and renaming, right? So here I am giving it in a pictorial sense. When you're giving it to a Turing machine, you may give the adjacency matrix or the adjacency list. So the matrix or the list, the order of the vertices may have been jumbled up. But just to make you understand, I am just drawing a pictorial version of graph isomorphism, right? So let us see. So 1, 2, 3, 4, 5 form a 5 cycle. So here we have to find a 5 cycle. So maybe why not this? So I will try to. The claim is that, let's say 1, 2, 3, 4, 5. So these form a 5 cycle because let me try to outline. Right, this form a 5 cycle, and the remaining vertices also form a 5 cycle. But then I have to be careful because 1 is adjacent to, in the blue graph, 1 is adjacent to 2, 5 and 6. So in the red graph, it should also be adjacent to 2, 5 and 6. It's already adjacent to 2 and 5. Now it should be also adjacent to 6. So which makes this vertex 6. Similarly, 2 is adjacent to 1, 3 and 7. It's already adjacent to 1 and 3. So this should be 7. 3 is adjacent to 8. Similarly, so this should be 8. 4 is adjacent to 9. So this should be 9. And the central vertex should be 10, adjacent to 5. So let's see how the inner, in the blue graph, how the inner star is connected. 6 is, so maybe I'll just write down here. In the inner star is 6, 8, 10, 7, 9 and back to 6. Right. So let's see whether the same thing is true here. 6, 8, 10, 7, 9 and back to 6. So indeed it matches. So this is why it's an isomorphism. So it is the same graph but just redrawn in a different way. And in fact, even this graph is a redrawing of the same graph in a different way. These two are both the same graph, the red and blue. What I'm saying is that the black graph in the right side, that's also another isomorphic graph, right? So that is a problem of graph isomorphism. Given two graphs, we have to decide whether they are the same. By rearranging the vertices, can we get one from the other, right? One from the other means the edges should be the same. So here 1 is adjacent to 6, 2 and 5. That is the same in the blue graph as well as the red graph, right? And there are evidences. So this is, we do not know a polynomial time algorithm for graph isomorphism, and there are strong evidences, meaning there are some results that indicate that this is not NP complete. Meaning, if this is shown to be NP complete, something else happens which is unlikely. Okay, so I do not want to get into that, but the point is that it is believed to be a problem that is not NP complete. Also, we do not know a polynomial time algorithm. So that is why people think this is an NP intermediate language. The another problem that is believed to be NP intermediate is factoring, right? So factoring is the problem of given a number, just to factor the number into prime factors. So that is this is not a decision version of the problem, but a decision version. There are maybe more than one way to write a decision version. One of such a way to write a decision version is to write like this: n comma k, where capital N has a prime factor that is at most k. So in other words, we are asking, does number n have a prime factor smaller than k? So for instance, sorry, I'll use another color, or maybe I'll use another color. So for instance, 51 10, this is a yes instance because 51 has 3 as a prime factor, which is less than 10. At the same time, 101 10 is a no instance because 101 is a prime number, so it does not have a prime factor smaller than 10. In fact, it does not have a prime factor smaller than 100 itself, right? And even this is a no instance, 121 10, right? Because 121 is simply 11 squared, so the smallest prime factor is 11, so it does not have a prime factor of size 10. Anyway, the goal is, you can certainly solve this, decide this in polynomial time if you can factor in polynomial time, but we do not know how to factor in polynomial time. So this is also a problem in NP, but we do not know whether it is, we do not know a polynomial time algorithm. Also, it is not believed to be NP complete. And maybe I'll just say the same thing for graph isomorphism also. Given, so it is, the graph isomorphism is also in NP. Given a mapping, it's easy to verify. If I tell you, you put 1 to 7, 2 to 8 and such things, like between the two graphs, if I say in G1 1, you can map it to G2 6 and so on, then you can verify that they are the same graph. But so it is an NP, but there is no known polynomial time algorithm. and also it is believed to be not NP complete. Same thing for factoring. So that is about NP intermediate languages and Ladner's theorem, which simply states that if P is not equal to NP, there are NP intermediate languages.